Imagine walking through a steaming hot spring in Yellowstone National Park, where vibrant colors paint the landscape, brilliant oranges, deep greens, and striking blues. These aren't just beautiful displays of nature, they're living signatures created by microscopic organisms that thrive in extreme conditions. Much like a detective finding fingerprints at a crime scene, scientists search for similar telltale signs across the cosmos. Not physical fingerprints, but chemical signatures that whisper, "Life exists here." These chemical signatures, or biosignatures, are nature's way of revealing life's presence. Think about our own planet Earth. Every breath we take adds to a complex atmospheric mixture that would look distinctly unusual to any alien astronomers studying our world from afar. The oxygen we breathe, the methane produced by countless organisms, and the intricate balance of gases in our atmosphere all tell a story of a living, breathing planet. Today, we stand at the threshold of an extraordinary journey into the search for extraterrestrial life. We're going to explore how life fundamentally changes its environment, leaving behind chemical clues that our advanced telescopes can now detect. From the latest discoveries about potential biosignatures in Venus's clouds to the mysterious organic molecules found on Mars, we'll uncover how scientists are piecing together evidence that could answer humanity's most profound question. Are we alone in the universe? We'll delve into the cutting-edge technology that allows us to analyze the chemical makeup of distant worlds, examining how the James Webb Space Telescope and other astronomical marvels are revolutionizing our search for life's signatures. We'll explore promising locations in our own solar system, from the icy moons of Jupiter and Saturn to distant exoplanets orbiting other stars, where conditions might be just right for life to exist and leave its mark. This isn't just a story about scientific discovery, it's a cosmic detective story where the clues could lead us to the most significant revelation in human history. As we embark on this journey together, we invite you to join our community of space explorers. By subscribing to our channel, you'll become part of a global movement of curious minds, all united in our quest to understand our place in the cosmos. Like the dedicated scientists who scan the skies for these biosignatures, we're on an ambitious mission to uncover the universe's greatest mysteries, one chemical signature at a time. Biosignatures represent one of the most fascinating frontiers in our search for extraterrestrial life. At their core, these are chemical or physical markers that can only be produced by living organisms. Nature's version of a smoking gun that indicates the presence of life. Just as a detective might use fingerprints or DNA to solve a case, astronomers and astrobiologists use biosignatures to search for evidence of life beyond Earth. Let's start with our home planet, Earth, which serves as our primary laboratory for understanding biosignatures. Over 4 billion years ago, our planet underwent a dramatic transformation known as the Great Oxidation Event. Before this revolution, Earth's atmosphere contained virtually no oxygen. Then, ancient microorganisms called cyanobacteria began performing photosynthesis, gradually flooding our atmosphere with oxygen. This massive change in Earth's atmospheric composition represents the first and most significant biosignature in our planet's history. This oxygen revolution didn't just change Earth's atmosphere, it fundamentally altered the planet's chemistry. The presence of large amounts of oxygen in our atmosphere is particularly telling because oxygen is highly reactive and would quickly disappear if it weren't being constantly replenished by living organisms. When we detect both oxygen and methane in an atmosphere, it's especially intriguing because these gases quickly react with each other. Their coexistence suggests that something, likely life, must be continuously producing them. Today, Earth showcases a wide array of biosignatures. Methane, although it can be produced by geological processes, is largely generated by living organisms on Earth, from bacteria in wetlands to vast herds of cattle. Phosphine, Another fascinating biosignature is produced almost exclusively by microbial life in oxygen-poor environments. We also see more subtle signatures, specific ratios of carbon isotopes that indicate biological processing, seasonal changes in atmospheric gases that reflect global-scale biological activity, and even the unique way vegetation reflects light, creating what scientists call the red edge effect. These modern biosignatures create a complex chemical fingerprint that makes Earth stand out as a living planet. The seasonal fluctuation of carbon dioxide levels, driven by plant growth and decay, creates a breathing-like pattern that would be visible to distant observers. Nitrogen compounds produced by bacterial activity, trace gases from plant growth, and even industrial pollutants from human civilization all contribute to Earth's biosignature portfolio. Understanding Earth's biosignatures is crucial because they guide our search for life elsewhere. When we study the atmospheres of exoplanets or analyze samples from Mars, we're looking for similar patterns and combinations of chemicals that, on Earth, can only be explained by the presence of life. However, scientists must be cautious. What indicates life on Earth might have different origins on other worlds, which is why we need multiple independent lines of evidence before we can confidently identify a true biosignature of extraterrestrial life. In our quest to find life beyond Earth, scientists have developed an impressive array of tools and techniques that would make any detective proud. At the heart of this cosmic investigation lies spectroscopy, our most powerful tool for understanding the chemical makeup of distant worlds. Spectroscopy works by breaking down light into its component colors, much like a prism creating a rainbow. When light passes through or reflects off a planet's atmosphere, certain wavelengths are absorbed by different molecules. This creates a unique pattern of dark lines in the spectrum, a chemical fingerprint that tells us exactly what compounds are present. Each molecule has its own distinctive spectral signature, allowing scientists to identify substances like water vapor, methane, carbon dioxide, and even potential biosignatures from billions of miles away. Modern telescopes have revolutionized our ability to detect these subtle signatures. The James Webb Space Telescope, with its massive 6.5-meter mirror and sophisticated infrared instruments, can analyze the atmospheres of distant exoplanets with unprecedented precision. Its specialized equipment can detect chemical components in concentrations as low as a few parts per million. The Webb telescope works alongside other powerful instruments like the Hubble Space Telescope and ground-based observatories, each designed to study different wavelengths of light and provide complementary data. However, finding a single chemical signature isn't enough to declare the discovery of life. Scientists require multiple lines of evidence, what we call convergent lines of evidence, to build a compelling case for biological activity. For instance, finding methane alone isn't conclusive, as it can be produced by both biological and geological processes. But if we detect methane alongside oxygen and observe seasonal variations in their concentrations, we have a much stronger case for biological activity, since these patterns mirror what we see on Earth. The challenge of false positives looms large in the search for biosignatures. History has taught us valuable lessons about jumping to conclusions too quickly. Take the famous Viking missions to Mars in the 1970s. Initial results suggested biological activity in Martian soil, but further analysis revealed these signals could be explained by non-biological chemical reactions. To avoid such pitfalls, modern scientists employ rigorous protocols and multiple verification methods. They look for chemical combinations that can't be easily explained by non-biological processes, study the context of their discoveries, and seek independent confirmation from different instruments and observation methods. Consider phosphine, a potential biosignature that made headlines when it was detected in Venus's atmosphere. Scientists approach this discovery with appropriate skepticism, demanding additional observations and alternative explanations before drawing conclusions. This methodical approach, while sometimes frustrating for those eager for definitive answers, ensures that when we do identify a true biosignature, we can be confident in our discovery. The future of biosignature detection looks even more promising. New telescopes under development will possess even greater sensitivity and resolution. Advanced spectroscopic techniques are being refined to detect more subtle chemical signatures, and artificial intelligence is being employed to help process the enormous amounts of data we collect. Perhaps most exciting is the development of instruments that can detect not just individual chemicals, but patterns of chemical behavior that could indicate biological processes. As our tools and techniques continue to evolve, we're entering an era where the detection of extraterrestrial life may move from the realm of speculation to scientific reality. Whether examining the icy plumes of Saturn's moon Enceladus or studying the atmospheres of distant exoplanets, these sophisticated detection methods represent humanity's best chance yet of answering one of our most profound questions. Are we alone in the cosmos? What biosignature would you be most excited to discover? Share your thoughts in the comments below. Would it be the discovery of complex organic molecules on Europa, signs of microbial life in Venus's clouds, or perhaps something entirely unexpected on a distant exoplanet? In our cosmic search for life, several intriguing destinations have emerged as prime suspects, each offering tantalizing clues that warrant deeper investigation. Let's explore these fascinating worlds and the evidence that makes them so compelling in our hunt for biosignatures. Venus, our closest planetary neighbor, recently sparked intense scientific debate with the potential detection of phosphine in its atmosphere. This discovery was particularly exciting because on Earth, phosphine is primarily produced by anaerobic bacteria and industrial processes. The harsh conditions in Venus's upper atmosphere, where temperatures and pressures are surprisingly Earth-like, could potentially harbor floating microorganisms adapted to the acidic environment. While subsequent observations have prompted ongoing discussion about the initial phosphine detection, Venus remains an intriguing target for biosignature research. The possibility of life existing in the Venusian clouds challenges our assumptions about habitability and reminds us that life might thrive in unexpected places. Mars, the red planet, continues to yield fascinating evidence of both its ancient potential for life and current mysteries. The Curiosity and Perseverance rovers have detected complex organic molecules preserved in ancient rocks, suggesting that the necessary building blocks for life were present billions of years ago when Mars hosted liquid water on its surface. Perhaps even more intriguing is the seasonal variation in methane levels detected in the Martian atmosphere. On Earth, most atmospheric methane is produced by living organisms, and the seasonal pattern on Mars hints at an active process that we still don't fully understand. While geological explanations are possible, the methane mystery adds another layer to Mars's potential for hosting life, either in the past or possibly in subsurface environments today. The ice-covered moons Europa and Enceladus represent another category of promising locations in our solar system. These ocean worlds harbor vast liquid water oceans beneath their frozen surfaces, kept warm by tidal heating from their parent planets. Enceladus, in particular, has provided direct access to its subsurface ocean through plumes of water vapor that erupt from its south pole. The Cassini spacecraft's analysis of these plumes revealed complex organic molecules and molecular hydrogen, suggesting hydrothermal activity similar to Earth's deep-sea vents, environments known to support thriving ecosystems on our planet. Europa, meanwhile, shows evidence of a similar ocean composition to Earth's, with recent observations suggesting the presence of sodium chloride in its ice crust, hinting at chemical processes that could support life. Beyond our solar system, the study of exoplanets has opened an entirely new frontier in the search for biosignatures. Scientists are particularly interested in planets orbiting within their stars' habitable zones, where temperatures could allow for liquid water on their surfaces. The TRAPPIST-1 system, with several Earth-sized planets in its habitable zone, represents one of our most promising targets. As we search these distant worlds, we're looking for specific combinations of atmospheric gases that might indicate biological activity. For instance, the simultaneous presence of methane and oxygen could suggest biological processes, as these gases would normally react and eliminate each other without constant replenishment. Recent discoveries have also expanded our understanding of what constitutes a potentially habitable world. Super-Earths, planets larger than Earth but smaller than Neptune, might have conditions favorable for life, different from what we know. Some scientists suggest that these planets could maintain their atmospheres and magnetic fields more effectively than Earth-sized planets, potentially providing more stable conditions for life to evolve. The James Webb Space Telescope is revolutionizing our ability to study exoplanet atmospheres, providing unprecedented detail about their chemical composition. This powerful observatory allows us to detect various molecules, including potential biosignatures, in the atmospheres of planets dozens of light-years away. Early observations have already revealed complex atmospheric chemistry on several exoplanets, though definitive biosignatures remain elusive. One particularly exciting aspect of exoplanet research is the possibility of detecting industrial pollution in alien atmospheres. The presence of certain artificial chemicals could indicate technological civilization, adding another dimension to our search for life beyond Earth. While such a discovery remains speculative, our improving detection capabilities bring us closer to potentially identifying not just biological signatures, but signs of intelligent life. Each of these locations offers unique possibilities and challenges in our search for biosignatures. From the acidic clouds of Venus to the ice-covered oceans of Europa, from ancient Martian rocks to distant exoplanets, we're gradually assembling pieces of a cosmic puzzle that may eventually reveal whether we share our universe with other forms of life. The diversity of environments under investigation demonstrates that life, if it exists elsewhere, might take forms we haven't yet imagined, adapting to conditions we once thought impossible for survival. The future of biosignature detection stands at an extraordinary turning point, with upcoming missions and emerging technologies promising to revolutionize our search for life beyond Earth. Let's explore the exciting developments that could lead us to one of humanity's greatest discoveries. NASA's Europa Clipper mission, scheduled to launch in the 2020s, represents one of our most ambitious attempts to search for biosignatures in our solar system. This sophisticated spacecraft will conduct multiple close flybys of Jupiter's moon Europa, using advanced instruments to analyze the composition of its icy surface and any material ejected from its subsurface ocean. The mission's mass spectrometers will be capable of detecting complex organic molecules that could indicate biological processes, while its radar systems will map the thickness of Europa's ice shell and potentially identify locations where ocean material reaches the surface. The Dragonfly mission to Saturn's moon Titan showcases how far our exploration capabilities have advanced. This revolutionary rotorcraft will launch in the mid-2020s, becoming the first vehicle to fly on another world. Dragonfly will explore Titan's unique environment, where liquid methane takes the place of water and complex organic chemistry occurs naturally in the atmosphere. Its instruments will analyze the Moon's complex chemistry, searching for potential prebiotic processes or even novel forms of life adapted to Titan's extreme cold and exotic biochemistry. In the realm of exoplanet research, the next generation of space telescopes promises unprecedented capabilities. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will survey vast regions of space, potentially discovering thousands of new exoplanets. Its coronagraph technology will demonstrate our ability to directly image planets around other stars, a crucial step toward detecting biosignatures in exoplanet atmospheres. New methods being developed for biosignature detection are equally exciting. Scientists are working on advanced spectroscopic techniques that can identify more subtle chemical signatures. Machine learning algorithms are being trained to recognize patterns in atmospheric chemistry that might indicate biological processes, potentially identifying biosignatures we hadn't even considered. These AI systems could analyze vast amounts of data from multiple telescopes, identifying promising candidates for more detailed study. Quantum sensors represent another breakthrough technology on the horizon. These incredibly sensitive devices could detect minute variations in magnetic fields or gravitational effects that might indicate subsurface oceans or geological activity on distant worlds. Such information would help us identify the most promising locations for biosignature searches. The development of new biomarkers is also expanding our search capabilities. Scientists are identifying novel chemical combinations that could serve as reliable indicators of life. For instance, research into anti-biosignatures, chemical conditions that would rule out the presence of life, is helping to refine our search strategies. Additionally, studies of extreme environments on Earth are revealing new potential biosignatures that could indicate life in conditions we once thought impossible. Among the most promising targets for future biosignature detection are the TRAPPIST-1 system's potentially habitable planets. The James Webb Space Telescope will conduct detailed observations of these worlds, analyzing their atmospheres for signs of biological activity. The detection of certain combinations of gases, such as methane and carbon dioxide in specific ratios, could provide compelling evidence for life. Closer to home, Venus is experiencing a renaissance of scientific interest. Multiple missions are being planned to study its atmosphere and surface, including NASA's Da Vinci Plus and Veritas missions, as well as private ventures. These missions will carry instruments specifically designed to search for biosignatures and understand the potential for life in Venus's cloud layers. Scientists are also developing more sophisticated models for understanding potential false positives. These models consider how geological and atmospheric processes on alien worlds might mimic biological signatures, helping us distinguish true biosignatures from natural phenomena. This work is crucial for avoiding false declarations of life detection and ensuring that any positive identification of biosignatures stands up to rigorous scrutiny. Perhaps most exciting is the development of sample return capabilities. Following NASA's successful Mars sample return mission planning, similar missions are being considered for other potentially life-bearing worlds. The ability to analyze extraterrestrial materials in Earth's most sophisticated laboratories would tremendously advance our search for biosignatures. Looking further ahead, proposed missions to explore the subsurface oceans of icy moons like Europa and Enceladus could provide direct access to environments where life might exist. These missions would involve sophisticated submarines or melting probes capable of penetrating the ice shells to sample and analyze the waters beneath. The future of biosignature detection is not just about individual missions or technologies, but about creating a comprehensive network of observational capabilities. By combining data from multiple sources, space-based telescopes, planetary probes, and ground-based observatories, we're building an increasingly sophisticated ability to detect and verify potential signs of life beyond Earth. This multi-pronged approach, coupled with advancing technology and refined search strategies, gives us the best chance yet of making one of the most profound discoveries in human history, that we are not alone in the cosmos. Throughout human history, people have gazed at the stars and wondered about the possibility of life beyond Earth. But never before have we stood at such a pivotal moment in our quest to answer this fundamental question. We are living in a truly remarkable era where the convergence of cutting-edge technology, scientific understanding, and exploration capabilities has brought us to the threshold of potentially discovering life beyond our planet. Consider this extraordinary moment in time. Our telescopes can now peer into the atmospheres of planets trillions of miles away, detecting molecules that might indicate the presence of life. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, can analyze the chemical composition of exoplanet atmospheres with a level of detail that would have seemed like science fiction just a generation ago. We're not just looking at distant points of light anymore, we're reading the chemical stories they tell us. What makes this moment even more extraordinary is the sheer number of tools at our disposal. We have rovers drilling into Martian rocks, searching for signs of ancient microbial life. Spacecraft are preparing to explore the potentially habitable oceans of Europa and Enceladus. Our radio telescopes scan the cosmos for signs of technological civilizations, while our spectroscopes analyze the light from thousands of newly discovered exoplanets. Each of these instruments represents a different way of asking the same profound question: are we alone? The pace of discovery is accelerating exponentially. In the past decade alone, we've identified thousands of planets orbiting other stars, found organic molecules in the plumes of icy moons, and detected potential biosignatures in places we never expected to find them. Each discovery builds upon the last, creating a web of evidence that brings us closer to potentially answering one of humanity's most enduring questions. But perhaps the most thrilling aspect of our current era is that we're no longer limited to passive observation. We can actively seek out biosignatures through targeted missions and increasingly sophisticated detection methods. The technology we possess today allows us to not only identify promising locations for life, but to actually test our hypotheses through direct exploration and analysis. This convergence of capabilities represents a unique moment in human history. Never before have we had the ability to detect the chemical signatures of life on other worlds, and our detection capabilities continue to improve at an astonishing rate. Every new mission, every technological advancement, every refinement in our understanding brings us closer to potentially making the most profound discovery in human history. We stand at the intersection of imagination and capability, where centuries of human curiosity meet the technological prowess to finally seek answers. This is not just about scientific discovery, it's about our place in the cosmic story. The detection of life beyond Earth would fundamentally change our understanding of our own existence and our relationship with the universe. The next few decades hold unprecedented potential for discovery. With multiple missions planned to explore potentially habitable worlds in our solar system, and increasingly powerful telescopes scanning distant exoplanets, we are living through humanity's first real opportunity to find evidence of life beyond Earth. Each new day brings the possibility of a discovery that would reshape our understanding of life itself and our place in the cosmos. This is more than just a golden age of exploration. It's the first time in our species' history that we have the tools, knowledge, and capability to scientifically investigate one of our most profound questions. We're not just dreaming about finding life anymore. We're actively searching for it with increasingly sophisticated tools and methods. Every observation, every mission, every new piece of data could be the one that leads to the greatest discovery in human history. The most incredible part isn't just that we have this technology, it's that we're using it right now, actively searching for signs of life beyond Earth. We're not waiting for some future generation to make these discoveries. We're making them ourselves, in real time, as our instruments scan the cosmos and our missions explore new worlds. This is our moment, our opportunity to potentially answer one of humanity's oldest questions, and we're living through it right now. The discovery of a definitive biosignature beyond Earth would mark one of the most transformative moments in human history, reaching far beyond the boundaries of scientific achievement. This revelation would touch every aspect of human society, from our philosophical and religious beliefs to our understanding of our cosmic significance. Throughout history, humanity has often positioned itself at the center of existence. The confirmation of life elsewhere would require a profound shift in this perspective, much like the Copernican revolution forced us to accept that Earth was not the center of the universe. This discovery would compel us to reimagine our place in the cosmic narrative, no longer as a unique manifestation of life, but as part of a broader biological tapestry spanning the cosmos. The psychological impact would be immense. Knowing we're not alone would create a new context for understanding human existence. It would affect how we view our struggles, achievements, and potential future. Some might find comfort in knowing we're not isolated in the vast cosmos, while others might feel challenged by the reality of sharing the universe with other forms of life. Religious and philosophical frameworks would face unprecedented questions. Many belief systems would need to adapt to incorporate this new reality, potentially leading to profound theological discussions about the nature of creation and our relationship with the divine. This could spark a renaissance in religious and philosophical thinking as humanity works to reconcile ancient wisdom with new cosmic revelations. The confirmation of extraterrestrial life would also significantly influence how we approach environmental challenges on Earth. Understanding that life can emerge and thrive in other worlds would emphasize the precious nature of all biological systems. This could strengthen environmental conservation efforts and deepen our appreciation for the interconnected web of life on our planet. In the scientific realm, such a discovery would open entirely new fields of study. Comparative biology would expand to include alien biochemistry, potentially revolutionizing our understanding of what constitutes life. Medical research could benefit from studying alternative biological systems, possibly leading to groundbreaking treatments and therapies inspired by extraterrestrial life forms. The political landscape would also transform. International cooperation might strengthen as humanity realizes its shared heritage in a living cosmos. The discovery could promote global unity, encouraging nations to work together in exploring and understanding our cosmic neighbors. Conversely, it might also raise new questions about planetary protection and the ethics of interacting with extraterrestrial life. Economic systems would likely evolve in response to this discovery. New industries would emerge focused on studying and potentially interacting with alien life. Space exploration would receive unprecedented attention and funding, driving technological innovation and creating new economic opportunities. Education would need to adapt to incorporate this new understanding of life in the universe. Students would learn about biology in a cosmic context, understanding Earth's life as one example among potentially many. This would foster a more inclusive and universal perspective on life sciences. The arts and culture would experience a renaissance as creators grapple with this new reality. Literature, music, film, and visual arts would explore themes of cosmic life, potentially giving rise to entirely new artistic movements and forms of expression. This cultural shift would help society process and internalize the profound implications of the discovery. Social media and global communications would play a crucial role in how humanity processes this information. The immediate worldwide sharing of this discovery would create a unique moment of global unity and shared experience, potentially fostering a new sense of human solidarity. Perhaps most profoundly, knowing we're not alone would alter our species' long-term aspirations. Space exploration would take on new urgency and meaning, driven by the possibility of finding and studying other forms of life. Our technological development would likely accelerate as we strive to better understand our cosmic neighbors. This discovery would also raise important questions about our responsibilities as a spacefaring species. How should we interact with other forms of life? What ethical guidelines should govern our exploration of living worlds? These questions would shape our approach to space exploration and our role as cosmic citizens. The discovery of extraterrestrial life would mark the beginning of a new chapter in human history. It would challenge us to grow beyond our terrestrial perspective and embrace our role as members of a larger cosmic community. This transition would be both challenging and enlightening, pushing our species to evolve intellectually and culturally in ways we can only begin to imagine. The search for biosignatures represents humanity's most sophisticated attempt to answer a question that has echoed through generations. Are we alone in the vast expanse of space? This quest transcends pure scientific inquiry, touching the very core of human curiosity and our eternal desire to understand our place in the universe. As we deploy our most advanced technologies and brilliant minds to detect these subtle chemical signatures of life, we're following in the footsteps of countless generations who looked to the stars and wondered. Today's hunt for biosignatures stands as a testament to human ingenuity and determination. From the powerful mirrors of the James Webb Space Telescope to the sensitive instruments probing Mars's ancient rocks, from the sophisticated analysis of exoplanet atmospheres to the planned exploration of icy moons, we're conducting the most thorough search for life ever attempted in human history. Each new discovery, each technological advancement brings us closer to potentially answering this profound question. The possibility that we might detect signs of life beyond Earth in our lifetime is both thrilling and humbling. Such a discovery would mark not just a scientific milestone, but a pivotal moment in human consciousness. It would forever change our understanding of life itself and our relationship with the cosmos. As we continue this search, we're not merely collecting data or analyzing chemical signatures. We're pushing the boundaries of human knowledge and understanding. Whether these biosignatures lead us to microscopic life forms in our solar system or hint at distant civilizations on faraway worlds, each discovery adds another piece to the cosmic puzzle. The answer, when it comes, will resonate through generations to come, marking the moment when humanity finally understood its place in a living universe. As we conclude this exploration of biosignatures and their profound importance, we invite you to remain part of this incredible journey. Your curiosity and engagement drive the scientific community forward, inspiring new questions and pushing the boundaries of exploration. By subscribing to our channel, you'll join a vibrant community of cosmic explorers united in our passion for understanding the universe and our place within it. Stay connected with us by hitting the subscribe button and activating the notification bell. This way, you'll never miss our upcoming adventures as we continue to explore the mysteries of space, from the latest exoplanet discoveries to breakthrough developments in our search for life beyond Earth. Each notification bell ring could be your alert to humanity's next great discovery in space. Your participation in this community matters. Through comments, discussions, and shared curiosity, we create a collective journey of discovery. Together, we're not just watching science happen, we're part of a global movement seeking answers to some of humanity's most profound questions. Join us as we continue to explore the cosmos, one discovery at a time. in our quest to understand if we truly are alone in this vast and magnificent universe. Remember, every great scientific discovery began with curiosity just like yours. By being part of this community, you're contributing to humanity's greatest adventure, the exploration of space and the search for life beyond Earth. Subscribe now to ensure you're part of this extraordinary journey. The universe is waiting to be discovered, and your next notification might just be the announcement of the most significant finding in human history. The journey continues, and we want you to be part of it. See you in our next exploration of the cosmic frontier.